Hello, I'm Xiang Hui, and today I'll be talking about the motivation, derivation, as well as an example of Euler's method. So, firstly, what is the idea behind Euler's method? So, as you can see, I can have a tangent line here given my x naught and my y naught, right? And if I use the tangent line at this point, I can try to approximate a value of my y if we don't know the curve. However, if we get further and further away from our initial starting point, it gets less and less accurate of a approximation. So the idea of Euler came up with an idea where at every step size, let's say we have a step size h, we create a new tangent line or a new line from the derivative of the curve here, given a x value and a y value, and we continue and we construct multiple lines till we reach our endpoint, our xn, our final x, and we find our y here. So that is the idea behind Euler's method. So now I'll go through a more formal derivation of it. So let our equation be in this form here, fxy, and we have our initial starting point, initial value problem right here. Let's define xi as y naught, x naught plus ih here, and we are trying to find the line of the curve at evenly spaced points inside this interval here. Xn is my endpoint and x naught is my starting point. So that is the key idea. And we can tell from recursion that xi plus 1 is equal to xi plus h, and we have our trying to find our error here, which will be important for later. Okay, so now we can use this equation here to find our tangent line, substituting our our gradient, to be the differential equation here, as well as substituting xi plus 1 into x and yi plus 1 into y, and also substituting in this recursion here, it simplifies very nicely and we get the equation for Euler's method. Now I'll go and upon the exact value of the example here. So we have this differential equation, separating the variables, integrating both sides, we can get this general solution, but we want an exact solution. So we find our constant of integration here, and plugging in x equals to 1, we can get our exact solution, the root of 11 over 3. So now let's go onto the Excel sheet. As you can see, I have my step size here, the n which is calculated by the reciprocal. And now this is my yn plus 1. So this is my yn, my step size chosen. And as you can see, I actually locked the step size chosen because I don't want it to go down. And this is my xn, and plugging in into the differential equation here, right? So what happens when, let's say, I choose a smaller step size, let's say 0.1, you can see that, let's compare our values from 0.2. 0.2, 1.90, not very close to our exact value. Let's go 0.1. You see, as I choose a smaller and smaller step size all the way to 0.01, the error actually decreases. So smaller the step size, closer it is to the exact solution, but also the amount of iterations we have to do increases very fast. For 3dp of accuracy, I have to iterate it 100 times, which is extremely inefficient. That's why we rarely use Euler's method nowadays, but it's a fairly simple approximation and allows us to approximate differential equations. Thank you for listening to me. Have very fruitful math ahead. Thank you.